In our day-to-day life, we use these six directions many times, and these six directions are up, down, right, left, front, and back. So, if you start from a point and you make arrows in all these directions of equal length, then what you get is an octahedral shape. So, we will discuss stereochemistry today in this octahedral shape. Many molecules in organic and also in inorganic chemistry have this kind of a shape, and we will see some interesting features about this kind of shape. So first of all, why this shape is called octahedral? So that can be understood if you join the ligands or the vertices or uh, the points where this shape finishes. So if you join them, and then you get an octahedron, and this is called an octahedron because it has eight faces. Octa means eight, and head means it's like your head face. So your face is on your head. Octahedron, eight faces. So you can count it here: one, two, and three on the back, fourth on the back, four up side, and four down side, which makes a total of eight faces. So 3D figures like this, they are often classified according to their number of faces. For example, tetrahedron has four faces, dodecahedron has 12 faces. So, and in terms of molecules, if molecules take up this kind of a shape, then there will be different kind of atoms, and this these groups which are getting attached here could also have many different atoms. But logically speaking, I will be denoting them with only those things which are important. For example, if it's a single connection, I will use only one sphere for that. Maybe it's like a CH3 group, but I am just using a sphere for that. And for same kind of groups, I will use same kind of sphere, and in the red here will be my central atom, and then different connections. These connections could be different, so I can use different kind of colors. For example, I'm also using green here, and if I have a molecule with all six different kind of groups attached to the central atom, then I will use six different colors like that. And sometimes if you have a bidentate ligand in coordination compound, for example, let's say suppose there is cobalt 3 plus ion, and it's getting attached with ethylene diamine. So ethylene diamine is something like this, and there, these are the two bonds, these are the two coordinate bonds which are being formed here. So I will use this kind of a notation for ethylene diamine kind of molecules which are symmetric because they are getting attached from same kind of atom, and they are interconnected. So I will use this kind of uh, this kind of an arrangement. And for symmetric unsymmetric bidentate ligand, this was symmetric bidentate ligand. For unsymmetric bidentate ligand, I will use something like this. They will be interconnected, but they will have different colors on the different ends. So this geometry can get very interesting, and let's try to see the stereochemistry. What happens, how to apply stereochemistry, what kind of what to think about now in this geometry. So one very simple idea how to start thinking about this kind of molecules is like, suppose you have a given structure. So keeping the structure same, how many different molecules can you make in any case? Suppose if you have this kind of a structure, by structure I mean connection of atoms. So you can't change the connection of atoms. You have to maintain the same connection of atoms. So here you have M in the middle, and six similar groups attached to the central M. So this kind of a molecule you can make, and I'm pretty sure nobody can think about in any different molecule from this, arising from this structure, right? There's only one. How about MA5B? So this time you have something like this. You have a green sphere and all these A's are denoted by blue spheres, and this is B. This is some other kind of a group attached to the central metal, ion or atom. So you can make only one here also, but if you are thinking of these structures, like what if the green was pointing below, then you can always superimpose it. You can superimpose this structure with this, and molecules like these, they are always moving in the 3D space. So there is no up kind of a thing, like there is no direction which is definitely up or something like that. So these are the same molecules. If you take an axis like this and rotate it, and you can bring this green straight up, and you will see that all of the groups will superimpose, and the whole molecule, this whole molecule is superimposable with this molecule, right? Similarly, all these molecules are superimposable with the first one which I made. So with Ma5b also we have only one molecule, right? Let's move forward. What about Ma4b2? Ma4b2. Let's make the first one at least. And the first one is like this. And then you can think of the second one also. In the second one, you see that the green are not opposite. Here the greens are opposite. Here the greens are not opposite. And no matter how much you turn this molecule or move this molecule, you will never be able to superimpose this molecule with this one. So these are two different molecules. Is there a third one? Well, is there a third one? What if somebody is thinking about this kind of a molecule? So I can you can superimpose it with this one. You just have to take this axis like this, and bring a green up. You bring this green up, and then all of these blues are adjusting themselves, and then you have to bring this green to the front side, and you will see that this is superimposable with this one. And you can try all other different kind of situations, but I'm pretty sure using this move, like if you imagine any molecule like this in which you have two green spheres, you can always bring the first green sphere up, then the other green sphere will be exactly opposite to it. If that is the case, then it will be superimposable with this one. If that's not the case, then the other green sphere is at one of these positions, these four positions. Then you can turn the molecule again and superimpose that molecule with this second molecule. So there are only two molecules with Ma4b2 structure, right? Now, what kind of isomers they are? So of course they are stereoisomers because they have same structures, but what kind of stereoisomers? So are they optical isomers? So I tend to think about this situation is in like if let's first check if they are optically active or not. So you see this question, is this optically active or chiral? So I have a separate video on chirality of molecules and chirality with simple objects, the link of which I will post in the description below, so that you can watch if you are not aware of what chirality is. So is it optically active or chiral? So for that you have to take a mirror image and check whether the mirror image is superimposable or not. So if I take the mirror image, and I can see it very easily that these two are superimposable. So this is not an optically active molecule. And what about the second one? Is it an optically active molecule? I take a mirror and then I take an image and I see, of course, this is also not optically active because these two are superimposable. So any molecule which has a superimposable mirror image will not be chiral, right? So no. So yeah, so these are not optical isomers. They will be treated as geometrical isomers. But that's fine. This is another kind of classification inside stereoisomerism, which I will go into detail in some other video maybe. But today I would like to talk about this thing. This is from Wikipedia. I saw this information, like what we are discussing here is the same thing. Ml6 has only one isomer, Ml5L, this is La and this is Lb, and then you see what we said as Ma5b has only one isomer, right? And when we come to this Ma4b2, we have two isomers, and still we don't have optically active like enantiomeric pairs. You saw, because the mirror images were those molecules themselves, they were not separate, like uh, you will have optical activity when you have a molecule and its mirror images different, and both these molecules will be called enantiomers, but we had the same superimposable mirror images. Anyways, so let's see, like we have so many cases here, and you can think about how many cases also could be possible and if they have covered all of them or not. But I will come to this last case, which seems to be the most difficult one, and I will explain this one so that you will feel confident about dealing with any of these cases which can arise, right? So let's go into it. The question is, how many stereoisomers are possible for complex MABCDEF? So first one is here, of course. I have used 6 different colors: pink, green, orange, yellow, black, and blue. So the first one is there, and then suppose randomly I make a different one, this one. So we will have to check, we will have to use our superimposition skills. We will have to master the art of superimposition, which is very very common, because in our day-to-day life we also superimpose things mostly. Like I have seen um, girls, they superimpose certain kind of jewelries and certain kind of things, because they compare. So people do compare, of course, and when you are comparing in very detail, you try to match two things and you check for their superimposability. So this is the same kind of thing which we are doing here with the molecules. With the molecules, and you can do it with the objects also. So let's see, is this molecule and this molecule superimposable? So I can see one thing: the green and the yellow are opposite, and here the green and yellow are not opposite, so they are not superimposable. How about this one? Is this superimposable with any of these two? Okay, the green and the yellow, they are matching. So let's check for more. The orange and the pink are opposite, the orange and the black are opposite, non-superimposable. So already we have made 3 molecules with this structure. Yeah, so how many more can I make like this? I have no plan, so I will never be sure, right? But anyways, this question is very much similar to the question of dice. So if you have seen a dice, then mostly we have dice in which there is 6, 1 2 3 4 5 6, and opposite to the 6 you always have a 1, and opposite to the 2 you always have a 5, and opposite to a 3 you always have a 4. Why so? I don't understand. I don't, because people like to follow, maybe people like to stick to certain kind of traditions. But if you break this tradition, and if you want to make a dice in any kind of like, you don't follow this rule and you think about how many dice are possible, right? It's the same question as how many stereoisomers are possible with complex MABCDEF, because in a dice also we have these 6 directions: up, down, left, right, front, and back, isn't it? Okay, so without any plan we will surely get lost. So let's have a plan. So we will use superimposition to solve this puzzle. So I will consider first of all infinitely randomly oriented models with 6 different ligands, and like this. Suppose they are infinite, there are many models like this. So because they are infinite, I hope that all the different molecules which are possible, there is at least one of them inside this infinite sample. And now I will use this I will command or to adjust them in a way, and suppose we have control over them, so adjust them in a way such that the green sphere is up And when the green sphere is up, then we will have 5 kinds of molecules, not 5 molecules, but 5 kinds of molecules. So in the first kind, the green will be opposite to the blue, the green will be opposite to in the second kind, it will be opposite to yellow, in the third it will be opposite to orange, in the fourth it will be opposite to black, and in the fifth it will be opposite to pink. Great. So we will have these 5 kinds of molecules. Let's explore the first kind, this one. Okay, in the first kind you will have yellow somewhere here, right, on in one of these 4 positions. So I will then command to adjust the yellow to be here. Okay, and then the situation simplifies. Then if the yellow is here, then let's say the black is opposite to it, then we get 2 molecules like this, right, the pink and the orange here, and then pink there and orange here. Similarly, if yellow and pink are opposite, then I can have 2 molecules like this, the orange and the black here, and the black and the orange here. And then I can have opposite to the yellow, orange, and then I can have 2 molecules like this. So these are the 6 possibilities which are possible in the first kind. So in the first kind we will have 6 molecules, right? And one more thing, it's like, it's, if you don't want to count and you know about circular permutations, so this is like in how many different ways can you circularly permutate 4 different things. So that would be 4 minus 1 factorial, which is 3 factorial, and that is 6. I would like to make a video on this also, because this is very interesting, permutations and circular permutations, why they follow this kind of formulas. So there's nothing to memorize in mathematics for sure. So but circular permutations, they have this we have this formula that for n different things we have n minus 1 factorial circular permutations. I will not go into the details of this of it in this lecture. So now we have 6 different molecules, and look at this, the second one just moved. Look at this, why? Oh, and then imagine there is a mirror in between these two, right? So this molecule is a mirror image of this molecule, right? These two are mirror images of each other. And then you look at the fourth one. The fourth one is the mirror image of the third one. So you see the black is here, and then suppose there was a mirror here, then the black will in the mirror image the black will be here, and in the mirror image the orange will be at the back side, in the mirror image the pink will be of course right, and in the mirror image yellow will be on the left, green will be on the top, and blue will be at the bottom. So these 2 molecules are also mirror images of each other, and they are of course non-superimposable, isn't it? Because here you can see we have been able to superimpose the green and the blue and the yellow and the pink, but these 2, they are not getting superimposed. So if now you make a move and turn any one of them around, then you can't hold on to these positions which are already superimposed, but you can try on your own. You will see that they will never get superimposed. Okay, so these 2 molecules are also mirror images of each other, and the last 2 ones are also mirror images of each other. So basically you have 6 possible molecules and 3 pairs of enantiomers, right? Great. And then let's come to the second kind. Let's explore the second kind. But this is very interesting, because you don't have to explore the second kind. The second kind is going to be exactly the same as the first kind. And the new molecules which you will get in the second kind will never be superimposed to the molecules which you got in the first kind, because in the first kind the green is always opposite to the blue, but in the second kind the 6 molecules which you will get will in them the green will always be opposite to the yellow. So they are also non-superimposable and definitely new molecules, and if you do the circular permutation you will get 6 molecules here also, and of course 3 pairs of enantiomers too. right? So that way it seemed like, or maybe it's not the right word. It felt like that this question was quite complicated, but if we went into the details, if you go into the details of the first kind, and then you see that okay, all the other cases are similar, and then you know the answer would be 6 plus 6 plus 6 plus 6 plus 6, 30, and 15 pairs of enantiomers, because each molecule will have a mirror image molecule which will have non which will be not superimposable on the first one, right? So this is what the Wikipedia table is was about. Let's see what was the table. Here we go. So we proved this thing: 30 isomers and number of enantiomeric pairs 15. Okay, in some of these cases you will see the number the number of isomers could be also odd and even, right? So this was the case which we solved, and here we got all the molecules had an enantiomer, but in some of these cases, in all the other cases, to be very frank here, like you if you have uh, here you have 6 molecules, and 6 into 2 is 12, but you have 15 isomers here. So there is something interesting going on in these kind of structures also, and maybe I will pick up a random one and make a video about that, how to understand this thing is like 15. Here you have 30, and don't think that the number of enantiomeric pairs will always be half, because there could be something interesting going on there. And that was also evident from what we discussed in the beginning of the video. In like the first 5 minutes we were talking about this Ma4B2 type of complex or molecule. In that we had 2 isomers but no enantiomeric pairs, right? So you also have an idea that okay, that is going to happen. And of course, number of isomers, odd number of isomers, we have also discussed. Very simply though, but I would like to make a video and about one of these random. I would like maybe this one, the second last one I will choose, and I'll make a video on this one also to explain how this can be possible. Thank you very much for watching the video, and for the viewers, I will ask a question for them to think. And this is a question from JE Advanced, no sorry, JE Mains 2016. Which of the following complexes shows optical isomerism? Okay, now you have a cis COEN. En is ethylene diamine. So the kind of structure which you will make here is like you have M and you have En. So you can connect this En like this, and then you have 2En, and this is cis. So if you connect 2En ethylene diamines like this, then and you connect Cl like this, you are getting a trans isomer. So we need to make a cis one. This is the second option. We need to make a cis one. So first you can have these 2Cls close by, and then you can think how to join the ethylene diamines. You can connect them like this also, right? So this is the cis isomer and this is the trans isomer, and then you have these possibilities also. So I would like the viewers to comment the answer of this question, because what they are asking is like which of the following complex shows optical isomerism. So basically not a well framed question, like okay, but that's fine. Optical activity, you just have to figure out which of these following molecules is chiral, and then if that is chiral, then they will have an enantiomer also, and they will show optical isomerism, right? So by the way, isomerism is a relation between two objects, and what if one of the molecules is optically active and the other molecule is not optically active, and they have same structure? What would you call that kind of a relation to be? Optical isomers or geometrical isomers? So then this classification of optical and geometrical isomers kind of crashes, and I don't think people who are setting up this question are aware of these things, or because it doesn't seem like they are aware of this thing. Thank you very much for watching the video. Have a nice day.